topic is magnet-eccentric rotation induces magnetic levitation. This is my teammate Shi Guo, and this is my teammate Wei Xie. My name is Qing Hai Bin. This study shows that magnetic levitation can be achieved using two permanent magnets. When one is rotating at a high speed, the other one will levitate and start spinning. There are two reasons why we choose this topic. First of all, levitation itself is fascinating and interesting. And second, as I mentioned, this phenomenon can be observed using two common materials, like two magnets and one high-speed rotator. The video shown below shows that the pendulum is equipped with a magnet, and when it starts spinning, the lower magnet will be induced in levitating. The upper magnet will be placed in a certain way that its magnetic moment is horizontally. And we want to investigate how the rotational speed relates to equilibrium point of the floating magnets. And we also want to introduce how the eccentricity affects the minimum speed for levitation. This is our setup. We construct our setup using mainly aluminum extrusion, and we use we set motor above the rotor, and finally we use a aluminum block to stabilize the rotor. And omega r is our rotor rotational speed. We drill a hole on the coupling such that it is slightly bigger than the magnet. And the eccentricity is defined as the magnet center position minus rotor center position. And the direction of the south side is positive. And we also use the counter to record the omega r. And this is how we measure and adjust our eccentricity. We use insulation tape to adjust the magnet eccentricity. And also, the trajectory of the center of magnets will form a circle, and the eccentricity is thus the radius.
Okay. The physics of this experiment can be written down in two equations. First is the equation of the moment, and second is the equation of the motion. And we focus on the equation of motion because it is related to whether the floater can levitate. And in the right figure, we can see that F dipole is the only attractive force on the floater, and the zeta change multiplying velocity of floater is the drag, and the mg is the gravity is the drag too. And this term is produced by the aluminum plates under the floater because it will produce eddy currents, and we use this term to model the eddy current damping. And F dipole is the dipole force for the rotor on the floater, and m is the mass of floater, and theta change is equal to 6 pi eta LRF is the analytical solution for viscous drag to model eddy current damping. And as I mentioned in the previous slide, the only attractive force is F dipole, and the F dipole can write down in these terms. And RF is the vector between the floater center and the rotor center. And today, if the eccentricity is equal to 0, just like delta is equal to 0, and the F dipole will remain this term because this is dot product is equal to 0 because it is vertical, and this term will be 0 too, and this term will be 0. So F dipole can be written down in these terms because it is smaller than 0, and its direction is dependent on MR, is horizontal, so it cannot levitate. Okay, then let's talk about our result. And in the bottom left video is the time-lapse video of our experiment, and this is with the omega r increasing over time. And as you can see, the floater is the vertical position of the floater is increasing with the omega r. And look at the right figure. The color in this figure represents the different delta, and as shown in the color bar. And under the same delta, when the omega r is increasing, the vertical position of the floater C increases too. Then just like the video showed. And this figure is the data when the delta is about 1 millimeter. Then we found that the trend of the data looks like the exponential. So we use an exponential equation to fit our data. And this is our fitting function. And the omega mini here is the minimum rotor speed for the stable levitation. And in the left, look at the left figure. The crosses here is the indicate the values obtained from the fitting result. And the blue and the red point is the omega mini in our experiment. And the color blue represents that the rotor magnet faces toward the S pole, while the red color represents face toward the N pole. And as you can see, when the absolute value of delta is rising, the omega mini will decrease and eventually approaching a constant value. And in the right figure is our simulation. This simulation is made from the equation in our series. And we can see that the trend of the simulation looks similar to our experiment. So this can make our experiment look more reasonable. And so in summary, we have three conclusions. The first, the larger the omega r, the floater levitates higher. And second, when the delta of the rotor is near zero, the floater is unable to levitate. And finally, within a certain range, as the absolute value of delta increases, the omega mini decreases and eventually approaching a constant value. Okay, then this is our reference and this is our presentation. And thanks for listening.